Hey there, everybody. Welcome back. This is Calculus 3, College of the Escolias, Fall 2022. We are in 13.4, which is on the differentiability of multivariable functions. We've shown how to find the differentials, find that they're derivative and continuous at specific points. We also want to be able to approximate something with like a local linear approximation. We talked about that in the first video. So we're going to go back and start with our delta f. It's approximately the partial of f with respect to x times delta x plus the partial of f with respect to y times delta y. And delta f is f evaluated at x naught plus delta x, y naught plus delta y, minus f of x naught, y naught. So we're going to do a little bit of magic here. We're going to make a substitution. I'm going to let x equal x naught plus delta x and y equal y naught plus delta y, such that delta x equals x minus x naught, delta y equals y minus y naught. We're going to replace these in up here, delta x, delta y, and in here. We're going to make those substitutions in there and see what happens. We've got f of x y minus f of x naught y naught is approximately the partial of f with respect to x at x naught y naught times x minus x naught plus the partial derivative of f with respect to y evaluated at x naught y naught times y minus y naught. If I move my f of x naught y naught to the other side, I have a function of f of x. I've got a function of x and y in terms of some starting point, and then the derivatives or the partial derivatives in each direction times a change. This could very much relates to what we've done in regular calculus. We had f of x is approximately f of x naught plus f prime of x naught delta x. This is just the scaled up version of that. So since we've got it written as f of x, y, we're going to call it the local linear approximation, which is L. So L of x, y is the local linear approximation to f at x naught, y naught. We need to have some initial point that we'll be doing it at. Okay. Let's take a look at an example. We're going to compare the error in approximating a function evaluated at 2.2 and 1.01 using a local linear approximation, where we approximate it from the 0.21. So something close by. We're going to approximate 2.02 and 1.01 using 2.1. Our function that we start with is xy times e to the xy. So we can see what do we need for this? We need the function at x naught, y naught. We need the partial derivatives evaluated at the same spot. And we need x minus x naught and y minus y naught. So let's get that going right here. F of x, y, our partial of f with respect to x and partial of f with respect to y. Calculated in here. Remember to use the product rule. And then evaluate at the point 2.1. We need them evaluated at our point. So the partial of f with respect to x evaluated at 2.1 is 3e squared. And the partial of f with respect to y at 2.1 is 6e squared. Notice that delta x is 0.02 and delta y is 0.01. We have everything we need up here. Let's write the linear equation first, the way, like the base form of it. Our local linear approximation is f of 2.1 plus the partial of f with respect to x at 2.1 times x minus x naught, which is x minus 2. And then we have partial of f with respect to y evaluated at 2.1 times y minus 1, which is y minus y naught. So if we do the local linear approximation, we're plugging them in. We had 2e squared, 3e squared, and 6e squared. The parcels are scaled by the deltas, and we get 2.12 e squared. Just to see how much the error is, we can compare it to the actual function evaluated 2.2 and 1.01, which would be 2.0402 times e to the 2.0402 power. Well, that doesn't mean shit to me. I don't know if it means shit to you. So what we do is we start in a calculator. So the local linear approximation is 15.6648. The actual function is 15.69352. And if we take a look at the error, I'm just subtracting L from F. So F minus L gives me 0.02872. And our percent error is E over F at 2.02, 1.01. So after making it a percentage, moving the decimal point twice, I got 0.183%. So it's not a big error. It's pretty good linear approximation. And now, why do we like that? These are just values times, it's a line. We got x to the first power, y to the first power. This is a linear approximation. The initial function was not. We had exponentials in there and stuff. It was ugly is the word we like to use in the business, or at least I do. That'll wrap up 13.4. Peace. I'll catch you on the flip side.